of 8259, which is very important. 8259 is called programmable interrupt controller. Right. So now let us try to discuss about how to interface 8259 with 8086 and what are the different operating modes of 8255 and what application, how can you get applications of 8259 is what we'll try to see in this particular class. So in the last class we have seen the 8254 counter modes, like after counting a sequence, there are 5 modes of 8254: mode 0, mode 1, mode 2, mode 3, mode 4 and mode 5. So I explained mode 0, mode 1, mode 2 in the last class. Mode 3, that is the software generator 2, square wave generator, right, square wave generator, and you can go ahead with the different remaining different modes. So now let us try to see 8259, which is very important IC. So the interfacing IC which we are going to deal now is 8259, and with your PC 80 systems, the computer usage of this is what we'll try to see, right? So I'll be discussing about what is interrupt and how many types of interrupts are there, and then when interrupt occurs in a given system, then what is the sequence the processor follows. Then we'll try to see how to interface this to 8086 and how to program 8259 for different applications. This is what we'll try to see. So now let us see what is interrupt. So interrupt is nothing but breaking a sequence. Interrupt is defined as breaking a sequences. Breaking a sequence is called interrupt. Now let us take example. When a teacher is teaching in a class and one student, he comes late to the class and asks the teacher, shall I come in? So then the teacher has to stop his or her lecture and attend the student, right, and allow him into the class. So that is interrupt. So interrupt, we can say, we can define it as breaking a sequence. Breaking a sequence is called interrupt, right? So why this is important? Interrupt and all, why it is important? So here is your microprocessor based system. In a computer, you can take an example. You have n number of devices. Right here you have n number of devices are connected. So CD drive, the number of devices are connected can be taken as you are copying something from computer to pen drive kind of thing, or into disk drive, a CD or pen drive. Okay, and then you will be connecting your computer to printer, right? So then you will be connecting this to a speaker. So different IO devices are getting connected to your processor. Then each device need to be serviced. Right. You are sending data to the pen drive, it is over, then you have to indicate it to the processor. So then how to service these many devices when the processor is interrupted by an output device, okay, input or output device, then how it reacts to that particular interrupt is now, let us try to see. So if you are working in this example, you can relate. So interrupt is an external event. Now let us say you are studying. Suddenly, if you are getting a phone call, then you have to stop your reading and attend the call and then answer them again, come back to your reading process. So it is a similar kind of operation, interrupt is. And now, as we discussed, there are n number of devices in a programmable system like computer. Then you can, so the different devices, like these many devices are there in your computer. 8155 is RAM with an IO timer, 8185 is 1K RAM, 8231 arithmetic processing unit, 8237 programmable DMLA controller, 8251 is programmable communication interface, 54 is timer, 55 is programmable peripheral interface, and 56 is multifunction universal asynchronous receiver transmitter, 59 is programmable interrupt controller, 8272 is single double density floppy disk controller, 75 is CRT controller, 79 is programmable keyboard display interface, 8295 is dot matrix printer controller, olden days, and 82720 is the graphic display controller and USART. Right. 8251A is universal synchronous asynchronous receiver transmitter. So these many devices you are connecting to the microprocessor to enhance the thing. So the microprocessor has to service different devices, then that can be done in two ways. One is polling and another one is interrupting. Right. So now let us try to see what is this polling and interrupt. Now let us take this particular thing here. This is polling. If there is a bucket, if the tap is, when the tap is coming, the water is coming through the tap, when the bucket fills, then this bucket, this water you used to fill the bigger bucket, right? So now while you are studying, it is like the water flow is little slow. So I'll check the bucket for every 5 minutes to see if it is already full, so that I can transfer that content to the bucket to the drum. So here you have a drum and here you have a bucket. So two processes you have to do at the same thing. So here you are the microprocessor here, and the input device is the bucket, and you are going to transfer this to the drum. So that can be as memory. So the instructions are, when you are studying, so studying is one instruction, and transfer the water to the drum is the second instruction. So this is the polling method. When you have n number of devices connected to the microprocessor, then the processor has to check each device. Okay, each device, the processor has to check each device then if there is any request from the device, it has to service that particular devices, right? So this takes longer time, right? So the processor time is getting wasted here. So here you have a number of IO devices. Then these devices can be taken up by the microprocessor. So the polling method is to test each IO device in a sequence to know if it needs any service. So thus a large portion of the main program is looping through this polling cycle in checking the conditions of IO devices. So then the processor valuable time is getting wasted. So now instead what you can do, you can put sensors, and when the water is filled up to the top, so then the sensor will give an alarm. So then I'll just study, and when the speaker starts playing music, it means that the bucket is full. So then I can then transfer the content of the bucket to the drum. So then what happens, you no need to go every time 5 minutes or 10 minutes. So water, how it is coming, you don't know, right? So then the moment the bucket is filled, then you just go and transfer the water into the drum. So this is what the interrupt thing is. So you are the microprocessor here. This is the input device, then the memory. So then the instructions are the same, study and transfer. But whenever there is a request or there is a need, then only we will attend that particular task. This is interrupt. So interrupt request is through the speaker is what you are getting through the input device. So the hardware polling necessitates, right? The hardware polling necessitates the source of interrupt is determined by some external circuit without involving the main processor and relieve the microprocessor from polling time. So now if you try to take one example on this polling and interrupt. So now let us try to take this example. If the peripheral is ready, so that means let us take there is a peripheral. Okay, let us take there is a peripheral, and that peripheral needs the request service of the microprocessor after every 10 milliseconds. So the 10 millisecond you can consider it as 10,000 microseconds, right? So every 10 milliseconds the peripheral needs service of the processor to do a particular task, which is of 10,000 microseconds is what you can consider. Then if the processor can, that means after 10 milliseconds, the processor can address that particular interrupt with 100 microseconds, then the moment the peripheral gives a request, then the processor goes and attempts the service which requires only 100 microseconds. So then the processor is free with 9,900 microseconds. The processor is free, right? So this much time it is getting free because of the interrupt sequence. In polling, what happens? It has to check regularly to the particular device, but the peripheral needs 10 millisecond service only, which is of 10,000 microseconds, but the processor can execute what is the requirement of that particular device within 100 microseconds. Then if it is used interrupt method, then only 100 microseconds is what it is need to service that particular request. So then the processor is free 9900 microseconds, right? So the processor no need to wait longer time with the device. The moment the device requires a request, then only the processor services it, right? So this is what the interrupt is. So the CPU is interrupted whenever the necessary microprocessor, and CPU serve many devices. So then the CPU is free the other time, so it can serve many devices, and it require more hardware. So coming to the interrupts, interrupt is a hardware initiated procedure that interrupts whatever the program is currently executing. So interrupts are useful when interfacing I/O devices that are provided or require data at relatively low data transfer rates. So here, when processor is doing a particular task, a main program, and keyboard, there is a keyboard. From the keyboard, the data is arriving. So then the process goes there and then it services. So the interrupt sequence is like this. So whenever there is a request by the device, the 8086 is interrupted through its pin INTR. So if there is a high on INTR, then if the processor, if it is executing in main program, and let us take there is an interrupt, then what it does is the current executed program will be stored in somewhere called the stack memory. The addresses of the main program is stored in ISR, interrupt subroutine, right? Then once that particular task, so it deviates there, it saves there, and then it executes that particular interrupt, and in the end it will execute an instruction called iReturn, interrupt return. So then the ISR content will be loaded, and then it is keep on executing that main program is. So this is execution. So in the process, what it does is, and the processor is executing a particular program. Let us take if there exists an interrupt. So then it pushes the flag content IF and TF to the stack memory. Okay. Then it pushes the code segment, the current address of the program, which is of CSIP combination, the physical address. Then it services that particular interrupt. In the return, when the processor is executing interrupt return, it pops up the content of IF and trap flag, and it pops up IP, CSIP, that means the current program execution address. Then it pops up the flag register, and then it's keep on start executing the previous programs. So then multiple interrupts. So processor, if it is, let us take a user program, high priority interrupt, if it is coming here, so then the processor breaks this particular sequence and it goes and executes this particular sequence. Then again, meanwhile, if you have one more interrupt, then it services that particular interrupt, and then it will be keep on executing. So this is sequential. Sequential means when the program, when user program, when the processor is executing, if there is an interrupt, so then it goes to that particular interrupt and then it executes that, and it comes back to the main program. And if there is one more interrupt, then it goes and then services that particular interrupt. So this is sequential. And nested interrupt is when the processor is executing the program, and if there exists any interrupt, so then the processor follows the as usual sequence which we discussed. It pushes the flag register, trap flag register into stack, and it pushes the CSIP content on the stack, and then it executes that particular interrupt is. Meanwhile, when it is interrupting, when it is executing that particular interrupt, if there is one more interrupt comes which is of higher priority than this, so then it goes to that particular interrupt and then it follows the same sequence and then it services that particular devices. So this is called nested interrupts, right? So the sequence is flag register content, CSIP content, right? It pushes, and this is what the interrupt sequence already we discussed it. So the relationship between INT and call instruction is here. Call, call is used to call the interrupt subroutines. So call is near pushes only IP, return near is its inverse. But interrupt pushes flags, CS and IP. Call pushes only the instruction pointer, right? Okay, so now coming to the types of interrupts, if you try to see, there are two types of interrupts. One is hardware interrupt and another one is software interrupt. Hardware interrupt means there are two pins with 8086. One is NMI and another one is interrupt request. So these are these are the pins available with microprocessor. So any device can interrupt the microprocessor through INTR or NMI. NMI stands for non-maskable interrupt. So non-maskable interrupt means when the processor is executing a program, then let us take the battery of your laptop. If it is getting dry, then the current execution status of the particular processor has to be restored. Then you will connect this to NMI, which is highest in priority interrupt, which is not maskable. That means if there is a request on this, all other requests will be made zero. Right, the processor will not entertain the other request, and it gives the high priority to NMI, and it saves the current content of the main program, and then that is how it saves the all the current executed instructions. And coming to, that means hardware is which you can touch. That means this is a pin where you can connect to that particular interrupt. That is called hardware interrupt. Coming to the software interrupt, these software interrupts are 256, and it is caused by execution of the interrupt instruction. Right. So when processor is executing certain instruction, then software interrupt. There is a possibility of software interrupt. So now let us try to see the example. Right, an example. Now, if you have, now you are using a division, you are using processor for getting division operation. So now, div-bl is the instruction you are using. Right, divide the accumulator with the content of BL if you are going for. If BL if it is having 0, so then it is divided by 0 kind of situation. So divided by 0 is undefined. So what the processor has to do when it comes across this kind of situation can be dealt with software interrupts. So then these software interrupts, like alert the processor of some hardware situation that means is a key has been pressed, a timer has expired, a network packet has arrived. So these are the examples. and same software calling protocol, right? And additional level of complexity with interrupt call not coming from your program code. So here you can use hardware interrupts. So as we discussed, the interrupts are INTR and NMI, which is non-maskable. And if that is a valid request, then the processor gives interrupt acknowledgement. So there are 3 pins related with interrupts, hardware interrupts. One is INTR, and another one is NMI, another one is interrupt acknowledgement. The processor acknowledges to the device, yes, I consider your request by using INTA. And the flag associated with this interrupt is the interrupt flag and the trap flag are both clear after the contents of the flag register are stacked during an interrupt. So the contents of the flag register and the location of IF and DF are shown here. When IF is set, it allows the INTR pin to cause an interrupt. And you can use a software STI instruction, set interrupt instruction to set interrupt. So when IF is set, it allows the interrupt pin to cause an interrupt. When IF is clear, it prevents the INTR pin from causing an interrupt. So you also can give a priority of these things. So in flag register of 8086, so these are available, right? So the interrupt flag is of this 9th, trap flag, right? Trap flag and interrupt flag. So when trap flag is 1, it causes a trap interrupt. Means type 1 interrupt to occur after each instruction executes. Trap is often called single step. When trap is 1, then the program is executed in single step mode, means it executes one instruction and it displays the register content and the flag register content. So when it is 1, it causes a trap interrupt, means type 1 interrupt to occur after each instruction is getting executed. So there are 2 instructions are used using with 8086. One is STI set interrupt, means it makes the IF flag to 1. And another one is CLI clear interrupt, means it makes the IF flag to 0. That means the processor can accept the other request too. So now coming to the software interrupt types, there are 255. So type 0, type 1, type 2. So there are 250 types of software interrupts are there. Example, assume that the interrupt service routine for the type 40 interrupt is located at an address of 2800H. So how do you write this address to the vector table? So here, we need to discuss about the interrupt vector table. So what do you mean by this interrupt vector table is, interrupt vector table is here what the processor has to do when there is an interrupt. So just now we discussed with interrupt vector, interrupt software interrupt, which is of divide by 0. So divided by 0 means this is type 0 interrupt. So type 0 interrupt means the CS content can be stored and IP content can be stored. So CS content, so the CS and IP content can be stored in the stack. So now if you consider this as a stack memory, so then the CS is of 16-bit and IP is of 16-bit. So you need 4 locations to store the content of CSIP. So then this we call it as interrupt vector table. That means the interrupt subroutines are written here. The interrupt subroutine means when there is divided by 0 occurs, what it has to do means that is written somewhere in the memory, and that memory's address is stored in a table in stack memory, and we call that table as interrupt vector table. Okay, interrupt vector table is right. So now let us try to see. And this interrupt vector table is to store the addresses of the interrupt service routines, ISR. An interrupt table, vector table contains 256 table entries. And each table entry takes 4 bytes, as we discussed now. CS and IP, which is of 16-bit and 16-bit, so it takes 4 bytes. And 2 bytes for IP value and 2 bytes for code segment register value. So then the interrupt vector tables locates in the physical memory 00002 003FF. So this memory you cannot use while you are doing programs. This is not available for the user. So that's why you will be starting with an address like in the lab 1000 and 000100 or some kind of thing, or 0100. From that particular point you can start. Right? So then now if you take an example, let us say there is type 40 interrupt occurred. So then this interrupt is located at an address 28000H. Calculation of that you can try to take. So then how do you write this address to the vector table? Means that CS and IP combination you can try to see. And similarly, so see this is divided by 0, no, that is an error. So here IP value 00 and 01 and CS value 02 and 03. So 4 bytes for this. Right. So like that, there are 255 types of interrupts, and you will be needing the total memory locations of 003FF. So this is what the location of interrupt vector table. Right? So then that is written as INTIN. INTIN, that N could be type 0, INT 0, 1, 2, 3 or so on. So this N is multiplied by 4 because each takes 4 bits, and in the address 4 and the offset address ISR is found, the interrupt subroutine is found. If you take an example, INT2 for the non-maskable interrupt. So whenever NMI pin is activated, the CFU jumps to a physical memory location which is of 00008 to fetch the CSIP of interrupt service routine associated with NMI. So when there is an interrupt, what it has to be done is written somewhere in some memory, that is called interrupt service routine ISR, and the addresses of those ISRs are loaded in interrupt vector table. And if you take an example of interrupt 2, then the address of that one is 00008. Right. So find the physical address of the interrupt vector table associated with interrupt 13 and interrupt 8. So then interrupt 13 into 4, that is a 52, that means 34H is the interrupt vector table address. Right, and then the physical address of interrupt 8 is 32, which is of 20H. So the memory addresses are 00020H to 0023H. Right, so this is for interrupt, it means 8th type of interrupt. So there are, the software interrupts are 255 types, like divided by 0, as here there is in a slide. this is divided by 0, and now when trap flag is 1, then it goes in single step debugging. So instead of single step debugging, what it has to do, it is written somewhere here in the form of ISR, and the ISR's address is this. And if it is 2, then 08002, 08009, that is what we have just now discussed. So what happens? The storing process is when user is writing some program, and if there is an interrupt, so then the processor saves the flag and return address in the stack memory, and it reads the ISR interrupt subroutine from interrupt vector table, and that goes to the ISR, and it executes this instruction and does the task what is needed for the interrupt. Then it comes, and in the end of the ISR there should be an instruction which is IRET, which is interrupt return. For every ISR there should be an interrupt return in the last. So when it executes this, so it loads the flag return content of CSIP, okay, from the interrupt vector table, right, and then it loads the flag, and then it executes that particular task. So the interrupts associated with instructions associated with the interrupts are CLI, clear interrupt flag, and set interrupt flag, STI, INT, this N is 0 to 255, and interrupt return, interrupt overflow, hard to stop, and wait. So these are the instructions related with this thing. And then coming to the special interrupts, type 0 is divided by 0, single step, type 2 is interrupt NMI, breakpoint is type 3, overflow is type 4, like that. So when AX is loaded with FFFF and CL is 10, and if you say divide CL with the content of the AX, then result will be 0 FFFH. So the result supposed to be stored in AL register is too large to store. So then what it has to do is it will try to store that in the combination, right, with some other register. So then at that case, what it has to do is what you can try to find out by using this. Now coming to the difference, what are the differences between these hardware interrupt and software interrupt is, the software interrupt is synchronous event with the program itself. Hardware interrupt is asynchronous. Any device can request service of the processor at any time. So this interrupt is requested by executing interrupt instruction, but this interrupt is requested by external device by giving a edge triggered or level triggered input at that particular INTR pin or NMI pin. So it cannot be ignored or masked, software interrupt, but it can be masked. So any device, if you don't want to service, so then that can be masked by using this. And it has highest priority among all interrupts. Software interrupts are highest priority among all interrupts. This priority is lower than the software interrupt is. So now coming to the priorities, INT 0 has highest priority, then INT 3 to INT 55 has the highest priority interrupts. Then NMI is the next priority interrupt, and INTR is next priority interrupt, right? So this is what the priority table of interrupts. Highest priority is INT 0 and lowest priority is your INTR. Now this table gives what exactly the processor does when there is an interrupt. So now let us try to take up when the processor is executing the current instruction and the current instruction execution is done, then what the processor it does is It samples for the interrupt. That means it checks there is an interrupt or not. So is there any internal interrupt or not? Means software interrupt or not. So then if it is yes, then what it does is it pushes the flags, it pushes the trap flag register, and it clears the interrupt and trap flag, because once the contents are pushed into the stack memory, they are cleared, and it pushes the CS and IP into the stack memory, and it calls the interrupt service routine, it executes that service routine, and then it will does that task what it has to be done, and it executes the user internal procedure, and if there is an interrupt return, so then it pops up the IP and CS contents, it pops up the flag registers, okay, into this thing, and then it will execute the next instructions. So this is the sequence you have to understand. It's very important. When processor is executing the current instruction and it checks for the interrupt. If there is a software interrupt, right, when it is executing, like, software interrupt kind of thing means, like, the example which you have considered here in the last slide. So when you are executing this AX with 10, the result is 0FF. So this result 0FF cannot be fixed in AL. So your AL will be having your result, AH will be having your reminder. But it is not fitting into this. So then it causes a type 0 kind of interrupt thing. So then what it does is it push the flags, then it is push the trap flag, then it clears the push flag and then trap flag, then CSIP content will be pushed on the stop, and then it calls an interrupt subroutine. Then when it is executing interrupt subroutine, it will come across the instruction interrupt return. So then when it returns interrupt return, then it from the stack, it get backs the content of CS and IP, and then it loads the flag register with the content of the saved content, and then it executes the next instruction. And it executes the next instruction, and then again it checks for software interrupts if it occurs. If there is a software interrupt, then this sequence it will follow. If there is no software interrupt, it is same simple kind of thing, move AL comma BL. So content of BL will move to AL. So then there are no software interrupts. Then it checks, is there any NMI? NMI means in the power failure cases, that NMI pin we are going to give it to this NMI pin, right? So then it checks for NMI. If there is an NMI, so then battery is okay, is what if you then feel. Then there is no NMI, then it checks for INTR flag. So the level of request, the priority is this. So then it checks there is any interrupt at INTR pin, right? Then if it is no, then it checks, is there any, it is of single step debugging, means trap flag if it is set or not. If trap flag is not set, then it executes the next instruction. Otherwise, if there exists any NMI, then it follows the same sequence. If there is an interrupt request, if it is yes, then it acknowledges that particular interrupt, and then it is ready to code and it does the same task. So then if there is a trap flag also, the content of these things need to be shown, so that it follows this particular subroutine. So this is very, very important. So then here what it does is, when processor is executing the current instruction, then it checks, like, is there any case of software interrupts at this case? No. If it is yes, then this sequence it will be followed. Then if not, then we try to see NMI, then INTR, then it will see trap flag, and then it executes the next instruction. So the priority table is this. So the highest priority is INT0, the lowest priority is single step debugging. Okay, single step debugging, which is of INT1, INTR1. So this is highest priority interrupt, and these are the lowest priority interrupt is. So the same sequence is written here. So the software instructions, or if there is no software type of interrupt, then it will check for NMI. If no NMI, then it checks for INTR. If there is no INTR request, then it checks for trap flag. And then if these are not there, then it executes the next instruction. So when the processor is executing these instructions, single instruction, we sample this kind of thing, whether it happens or not in the sequence. So if we take an example here, if you get a divided by 0 kind of error, then it follows this thing. So it pushes the flag content, it pushes the CSIP content, it clears the TR flag and IF flag, and it controls the transfer to ISR. And then when ISR is done, then push the flags CSIP, then it executes the next instruction as. Right? So this, like now up to now we have seen how interrupt occurs and how the processor services the request arised by different devices. So this task can be done. So here, coming to the hardware interrupts available, only one hardware interrupt is available to you, that is INTR. But if there are more number of devices, they are there in the given system, so then that can be serviced through a chip called 8259. So that means, so now what is 8259? So 8259 is when there are more number of devices are getting serviced. So then this 8259 has, it is called programmable interrupt controller, PIC, programmable interrupt controller. So 8086 has only one INTR pin. So then, but 8259 has 8, 1, 2, 3, 4, 5, 6, 7, 8. So IR0 to IR7, 7 other hardware. That means this 8259 provides a facility to the 8086 processor by providing 8 requests. Right? That is what 8259 is, programmable interrupt controller. Here you have 8 interrupts is what you can connect to 8259. Not 8. 8259 has a pin called SP. Right. So when it is connected to ground, it can be master's mode. In master's mode, it can accommodate through each one again 8. So 8 8259s you can connect. That means 64 hardware interrupts is what you can connect to the 8086 based processor is. Right. So that is what the significance of 8259. Right. So is this clear? So what is 8259? 8086 has only one hardware interrupt pin. Then there are two, NMI and INTR, but devices can be connected to INTR because NMI is used for most important tasks, right? So then here we are going to connect different devices to the 8086 by using this 8259 is. So 8259 is an interrupt controller. It connects the other devices to the microprocessor so that they also can be getting serviced. So that is what we have seen up to now. That is 8259 And now let us try to see the hardware details of this particular programmable interrupt controllers. So this is what we discussed now. So 8086 has only one INTR pin. So additional 8 devices we can connect using 8259. So then how it is connected to the processor or this thing means, so here what we have discussed up to now, it is shown in the form of diagram. So this is your 8086. It has a pin called INT. So here the interrupt controller, what it does is it provides other hardware interrupts. So there is a valid request from these devices. So then this gives an interrupt acknowledgement, and so that the interrupt, that particular interrupt is directly connected to the processor. So it is a intermediate device between your output and input devices and then the processor is. So if there is a request from the device, then INTR of CPU will go high, then the CPU will give interrupt acknowledgement. So then that particular device is serviced by the CPUs by accessing interrupt vectors and your stack memory kind of thing. So 8259 is a programmable interrupt controller, and it is a tool for managing the interrupt request, and it is very flexible peripheral controller chip, and it is used in computers, PC XT, external technology, and two PICs are connected. How that is and all we'll try to see now. So now the block diagram of 8259, if you try to see, the programming of 8259 in different modes can be set by writing a word through the database to the data bus. So this D0 to D7 is connected to D0 to D7 of your microprocessor, right? And to read into, right, to write a control word into the registers like in service register, interrupt request register. So the hardware interrupts which are there, by which we are going to connect the other devices are connected through interrupt request registers. So interrupt request register means I can take the example like this. So here CD drive is connected, here pen drive is connected, here speaker is connected, here, okay, printer is connected like that. So IR0 is given the highest priority and IR7 is given the lowest priority. So if there is a request from the device, then this interrupt request register identifies where the request is. So then there is a priority resolver. So it gives the priority, IR0 is given the topmost priority, IR7 is given the lowest priorities. So if there is any interrupt request in IR3, when IR0 is getting executed by one device, so then that particular thing can be masked. So it can be masked by using interrupt mask register. So there are three registers associated with 8259. One is in service register, and another one is interrupt request register, and another one is interrupt mask register, IMR. And this priority resolver, this gets the priority that one device. Now let us take, you are copying the data in your CD drive. If there is a request from the printer to give character, so then if printer is given the high priority, then now the current task is masked and then that will be given the high priorities. So that is what, so to write the control word into these registers, we will be using data bus buffer. And reading or writing into these registers can be done by using three pins. One is read bar, write bar, and A0s. The selection of the resistors, internal resistors of 8259 can be done by using 80. So what is 80? 80 is used to select registers like initialization command words, ISW, and operational command words, OSW. Right? And read bar and write bar in combination with I0 by M bar is used to read the content of this resistor or write into the contents of this resistor by using this. And there are three pins. One is CAS0, CAS1, CAS2. That means 18259. That means you are connecting 18259 to the 8086. Then this pin SP by enable pin, SP by enable. If it is connected to 5 volts, then this 8259 is worked as master's mode. It can be used as master's mode, in master's mode. And if it is connected to ground, then only 8 interrupts you can connect. I repeat, here, if this 8259 pin SP by EN is connected to 5 volts, means it is in master mode. In master mode, this IR0 is connected to one more 8259. So 8259 has 8. So 8 other interrupts it can accommodate. Then similarly you have IR1, IR2. So each one be connected to 8 8259s. So 8 into 8, 64 hardware interrupts you can provide by using 8259 in master's mode. So then what you have to do here, you have to connect this SP by EN in 5 volts, then you can use this in master mode. In master mode, each IR0 can be connected to one more 8259, and that one 8259 accommodates 8 hardware interrupts. 8 into 8, it becomes 64 hardware interrupts is. So now this is what we have seen, the pin diagram. So the pin diagram, the important pins are chip select, then read, and then write A0 and CAS1, CAS2 and CAS3. The CAS1, CAS2, CAS3 are used in master's mode only. If it is not used in master's mode, those pins are not used. Then we have seen this ESP by INDA. So these are the pins, and now this is what the in detail of 8259. So now if you try to see, this is the block diagram of 8259, which is a 28 pin IC. It is a 20 pin IC integrated circuit. So here you have VCC, here you have the ground. And we can write into or read from this 8259 resistors by using D0 to D7. So this D0 to D7, you have to connect it to D0 to D7 of your microprocessor. So then this is write bar and read bar. This is the chip select pin. That means if there is a 0 here, then only you can access 8259. Otherwise you cannot access 8259. And then this is CAS0 and CAS1 and then CAS2. These three pins are used to, these three pins are used when in cascading mode, CAS. And then 18259 provides 8 hardware interrupts, IR0 to IR7. Then here, if there is a request from any one of the devices connected to these IR pins, then this INT pin will become high, and this INT pin you can connect it to INTR of your 8086. Right? So almost all the pins we covered, and the functions of this thing we have seen. So this D0 to D7, chip select, read bar, write bar, and then A0. So then this is one more important thing is this A0. So 8259 has 4, that means ICWs, initialization command words. If you want to use this 8259, then you have to write into registers. There are 4 registers of ICW initialization command words, and 3 are operational command words. So then these 4 registers and 3 registers can be accessed by giving port 0 and port 1. That means these registers can be considered as port 0 and these registers are considered to as port 1. That means 8259 can be accessed through giving 2 port addresses, port 0 and port 1. So then this is about the registers, interrupt request registers. So this interrupt request register, it takes an interrupt from any external device. Here, it is very clear. This takes any interrupts from an external device, 8 external devices. So then this interrupt request register, it stores like, that is, from which device the request is coming. Then this priority resolver will resolve the priority among these. Right. Then there are different modes of operations of 8259, like fully nested mode, this mode. That means any one of the device can be given highest priority. So then this priority resolver will resolve the priority among these interrupts, and then this in-service register holds the status of this particular request. And by using interrupt mask register, you can mask any one of the interrupt if it is needed. Right. And then when there is, so the working is like this. When there is a request from any device, then the priority resolver resolves the priority of this. If it is a high priority, it makes the INTA pin high, and this INTA is connected to INTR of your 8086. If it is a valid request, then it gives an acknowledge signal on INTA, interrupt acknowledge, and then this interrupt acknowledge, right, when there is an interrupt acknowledge given by the microprocessor, that particular device is connected to the microprocessor through this D0 to D7. That means that is going to be connected. Yes. So this is the working. So in-service register are used to store all the interrupt levels which are being serviced. Okay, that is ISR. Each bit of this register is set by the priority resolver and reset by the end of the interrupt command word. And the priority resolver determines the priority of the bits set in the IRR. Okay, interrupt request register. This is what the working of 8259. And now, if you try to see the use of this A0, if chip select is 0 and A0 if it is 0, then initialization command word 1 is chosen. And if chip select is 0 and A0 is 1, then ICW initialization command word 2, 3 and 4, they are chosen. And when CS is 1 and whatever it is 0 or 1, then 8259 is not enabled. Yes. This is what A0 function. So coming to the interrupt sequence, just now we have seen the interrupt sequence and operation. So we can summarize the things what we have discussed up to now. One or more IR lines if it is go high, then corresponding IR bits are set. So then the 8259 evaluates the request and sends INT to CPU, and then the CPU sends the interrupt acknowledgement bar, and then the high priority ISR is set in interrupt request register. Okay, interrupt service register. Then 8259 releases call instruction on the data bus. Then call causes CPU to initiate 2 or more INTA bars. Then 8259 releases the subroutines addresses first low byte and then high byte. And ISR bit resets depending on the mode of operation is. So this is what the sequence. And now coming to the programming of 8259. So up to now we have seen what is exactly the interrupt. Then we need, different devices need to be serviced. Then we use 8259 to provide more hardware interrupts So then 8259 can be initiated. That means, it can be used or programmed by writing control register into two registers. One is initialization command words. This is ICR, and operational command word OCRs. Right? So now, before going to program 8259, now let us try to see the interfacing, how it can be done. So this is what your 8086 and AD0 to AD7 are connected to D0 to D7, and INT pin of 8259 is connected to INTR, and interrupt acknowledge of this one is connected to interrupt acknowledge of 8259. Right. So this is what the connection, and now and giving addresses to 8259. This is more in detail. So now the same thing, D0 to D7 are connected to D0 to D7, and read bar, write bar are connected to read bar and write bar. Possible, this is with I0 by M bar. In decoding logic you have to provide here, and that is connected to read bar and write bar. Here see M by I bar. So it is a decoder, and this particular device is decoded. So the output of this one Y0 is connected to CS bar of 8259. So if it is, if it is used, if it is connected to 5 volts, then it can be used in, then you will be using these particular pins. So now here, if you try to see this particular example, so this A0 to A15. So now if you try to see A0 to A15, so A4 to A15, so A4 to A15 are all ones. A4 to A15. So that means this should be 0. This should be 0 means this is logic OR gate. So this A4 to A4 R. Sorry. Here, this is, you have to get 0 here. So when all are 1, this is NAND logic. So all are 1 means the output is 0. So all are 1s. So the all are 1s is what it is written here. So A4 to A15 are all are 1s. So 4 bits F, next bit 4 bits F, next 4 bits F. So then A2, A3 and A1, A0, they are connected where? Now let us try to see. A0, so here you have an A0 and A0, where it is A0 is connected. So A0 of this one is connected to A, right, and A2, A3 are connected to BC. The 74LS 138 is a decoder, and then these particular logics, B and C can be, so can be 0, 0, so 0, 0, and then don't care, so then the address will be FFF0 and FFF2. So total 8259 can be addressed as two port addresses. So if it is interfaced like this, then the address is FFF0 and FFF2. Right? So similarly, you can take this as an example. Right. So this is what interfacing is. So now a simple problem can be given like this. Interface 8259 programmable interrupt controller to 8086, and that port addresses should be 70. You can give 8-bit port address or 16-bit port address. So then here see how to connect these things. So here you are using 74LS138 is a decoder, so which has to be connected to chip select. So address should be 70. So address should be 70. So 8259 is connected with microprocessor always in the even bank. So now here if we try to see, right, if you try to see A0 to A7, right, 70. So here A4 or 7 is what? 0, 1, 1, 1, 7. Right. And then A3, A2, A1. A3, A2, A1 are connected to the select lines of your decoder. Right. So that can be 000 and 001. This A1 can be, so this A1 can be two addresses. It can be 0 and it can be 1. So the address is 70 and the address is 70. So port 0 address is 70 and port 1 address is 72. And here you can use a simple gate logic to try to interface this 8259. So this is this is a simple thing which we are discussing from long back. So interfacing, you have to interface one 8259 IC to 8086, but the address should be 70. So a 70, that means it has considered as two ports. One port address is 70, another port address is 72. So then here 7 means A7 to A6, A5, so 111. So those pins are connected straight away. Another are not get, through not get they are connected. So the here output is 0. That means when it is considered as 70, then it can be made as 1. But whereas there is one more pin like A1 pin. So this A1 pin is connected to A1 pin of 8259. So this can be 1 or 0. So then 0, if it is 0 means this is 70. Then if it is 2 means 72. Right. So yes, even it is saved as even bank. So then the A0 bit is 0 only. So then here you can interface your 8259 now, and you can draw a clear-cut detail, right, like this. So you can, in minimum mode of 8259, so all other signals which we are know up to now, and M by IO bar and read bar and write bar are given to latch. So then you will be getting read bar and write bar straight away connected to read bar and write bar. And INTR of this particular thing, 8259 is connected to INTR. And interrupt acknowledge of this one is connected to interrupt acknowledge of 8259. And this is what a simple decoding logic. Now what we have seen, you can connect here and straight away you can connect the A1 to the A0 of 8259, and all other pins are connected to chip select. All other pins are connected to chip select. Right. So this is what simple interfacing is. So this is one more example, interface 8259 PIC with microprocessor, and write the initialization routine for 8259 to be vectored from type 40. The IO ports of 8259 should be selected 24H and 26H. And IR5 of master should be masked. So these kind of examples can be given, right? So then you can think of now giving addresses. 24 is what the address we have to give, 24 and 26. So 24 and 26 means now you see this is 2, this is 2, this is 2. So 4 means no, here this should be 1, and 0 1 0 0 is 4, right? 0 1 0 0, but A1, this one can be 0 and 1. So that two addresses you will be getting 24 and 26. So this you connected to chip select of your 8259, and rest everything will be same. So this is what just interfacing, and then mode of operation of 8259 can be seen. So coming to the operating mode. So the operating mode can be fully nested mode or automatic rotation mode, special fully nested mode, specific rotation mode, and special mask mode. So then pole mode. So there are 8259 can work in these modes. 1, 2, 3, 4, 5 and 6 modes it can work. In polling mode also it can work. I discussed what is polling and fully nested mode. So only I will take up fully nested mode and I will go ahead. So then automatic rotation priority mode. Automatic rotation priority mode, now if you consider this way, so what it does is, in fully nested mode, in fully nested mode, what we can do is, we can assign in fully nested mode, IR0 is given top priority, IR1 can be given next priority. So this is priority 1, priority 2, like that. And automatic rotation mode means, you can decide like out of this. So this is what, when it is starting, and 5 6 7 0 1 2 7. So IR2 is service. When IR2 is service, if there are 8 requests at a time, So then in fully nested mode, this IR0 is first service, then this, then this, then this. So when IR1, when it is serviced, so then IR5, if there is a request which is high priority, so then IR2 will be serviced next. Next IR5 will be serviced next. So there is an automation priority, and specific rotation priority means, right? So this is considered as highest priority and lowest priority, but we can change the priority levels. So now coming to the cascading of, so now we have seen interrupt, the details of 8259 and interfacing of 8259 with 8086, then how to cascade different things by using different 8259s using this is what now let us try to see. So here 18259, this is 18259, and this N8259, the SP, if it is connected to, here in a, so this is what your 8086, then this one is your master 8259. So this master 8259 means you have to connect this SP point to plus 5 volts. So then here 8259 here, if it is worked as in slave mode means you will connect this SP by EN bar pin to 0. So it will be in slave mode. So one, by using one, then we can accommodate 8 other interrupt requests. So now if you try to see, this is connection of two 8259s, how it is done in the computer. 8259s, two 8259s. So here if you try to see, this 8259 is worked as one master, and just now we have seen the interfacing, like how address will be decoded and connected to chip select. D0 by D7 is connected to D0 to D7 of the processor, and INTR is connected to INTR of 8086, INTA bar is connected to INTA bar, right? And then when it is connected to 5 volts, then it is in master mode. When it is master mode, then there's cascading pins of CS0, CS1 and CS2 are connected to CS0 and CS1 and CS2 of 8259. So this is in slave mode. So when it is in slave mode, then the SP by EN bar will connect it to 0. So it is in slave mode. So D0 by D7 of these things are connected to D0 by D7, and IR2 is connected to INT. So here using this, hard disk controller, coprocessor, different things, if there is a request on this, then that particular bit will be set, then that will set INT, then that will set INT here, and that will set INT here, and 8086 processor can be brought in. So this is one 8259 connection. Similarly, you can connect 8 8259s. Each pin you can connect, one more 8259, one more 8259. So 8 8259s you can connect this. So this is how it can be. This is our 3 8259s cascading with 8086. So this is what your microprocessor, this is what your 8259, so this is what your 8259, this is what your 8259. So let us take it is connected to IR1, and let us take this is connected to IR4. So like that, you can connect 8 8259s, and then you can do the cascading. So this is in detail, the microprocessor interfacing in detail. So now I'll give you this diagram. So then what you do is you identify the address to which this 8259 is connected in, and then how they are connected in cascaded mode. So 3 8259s are connected, 1, 2 and 3. One can be used in masters mode, another, this can be used in masters mode, these two can be used in slave mode. So 3 8259s are connected to 8086 processors. So this is how you can connect, and then the different addresses of these things. Now by seeing this A15, right, A15 to A14, they are anyhow one, and then this A3, A2 and A0 are chosen to select Y0 is this, Y1 is this, and Y2 is this. So you want to select this, or you want to select this, or you want to select this. That depends upon the select lines, right? A0, A2 and A3. So when they are 1 and 1, then only this is getting selected. So then this is G1 bar, right? So 74LS136 is. So then the address of that can be given as FFF0, FF2 and all. So this is how you can cascade different 8259. So now let us take this, show the schematic connection of one master and two slaves of 8259 programmable interrupt controllers with 8086 microprocessor. Write an initialization program to satisfy following conditions. So this is important, and up to now I discussed only the 8259 need hardware interfacing and cascading. Now we can see, one or two examples you can given. So vector type should start at 68H. That means, the interrupt which is occurred is of 68H. So it is a positive edge triggered, and IR4 or IR7 they are master expanded by slave. IR6 of slave 7 should be masked, and the IO port addresses can be starting with 80. So starting with 80 means now here if you try to see 80, so then 80 equivalent 10000. So this is 1000080, and then these are connected. So 80 or 81. So then 8259 these many addresses, another 8259 these many addresses, and another 8259 these many addresses. So addresses starts with 80, 82, 84, 86 and 80H, and then you can connect this, right? So this Y0 can be CS0, CS1 and CS2, and then you can draw the diagram like this. So here this is how you cascade your 8259s, and in the next class I'll try to discuss like how to 10 to 15 minutes is sufficient to know like how we can go ahead of initialization commands for this, which is of taking 10 to 15 minutes. As the time is now over, now let us review back what we studied. So we have seen, right, we have seen what is interrupt and what is interrupt vector table, how you are getting connected this, right? So then cascading mode, the hardware details of 8259 is what we have seen. So in the next class I'll just try to take up an example, and then how to program 8259 by using initialization command words and operational command words is what we'll try to see in the next class. Okay, is it all right? So then we'll move to the next topic in the next class. Within 10 minutes I'll be finishing this 8259, and next class I'll be dealing with DMA controller, so that our third chapter is going to be finished. So thank you.